All right, so Han Wu today is going to give the last talk of the session. So Han is a PhD student at Stanford right now, and so he's going to tell us about his work on Thompson sampling with unrestricted delays. So, yeah.
Thanks for the introduction. I guess we'll be having a detour on the games, because I won't be mentioning the word game anymore. So this work is about Thompson sampling with unrestricted delays, and this is a joint work with my advisor, Stefan. So brief agenda, I will sort of introduce this problem and motivate why we want to study this problem, and some theoretical results following that, and some extensive experiments showing the performance of Thompson sampling under these scenarios. So introduction and motivation. The standard framework for sequential learning involves a tight feedback loop, where each time step an agent chooses an action, sees the corresponding reward, and then updates their beliefs. However, in many real-world settings, the assumption that rewards are reviewed immediately following an action is not applicable. So I just list two examples here. For example, in a clinical trial, it may take time to assess whether a patient has responded to the given treatment. And in an email marketing campaign, it may take time to see whether a user clicks on an ad or not. So there are some existing work on delayed feedback under this scenario. But they make strong assumptions. For example, the first, one of the earliest results on delays, the 2011 paper by Dudek, they assume the delays are constant. And 2013 paper by Jolani on online learning with delayed feedback, their results depending on this expectation of the delay distribution. So the delays have bounded expectation. And also following that, there's 2018 paper on best arm identification when you have delays, and they assume the distribution of delays is known from previous data. And there's also a recent paper, 2020 paper, they assume the distributions of the delays have polynomial tail decay, and they use that information to construct upper confidence bound. So we will work with the standard stochastic multi-arm bandit scenario with delays. So the model is like when for each time t, agent will pick an action, and the environment will sample the reward from the reward distribution of that particular arm, and also samples a delay from the delay distribution of that particular arm. So agent will get a reward of RT, but it's not immediately reviewed. But the agent will get to the set of pairs of the action and reward, which contains the values of the action and reward pairs from previous rounds. And there's an implicit assumption in this model. So we actually assume the delays are independent of rewards, and I will mention that later. So we will evaluate our agent by the expected pseudo regret, called regret here from here on, and it's just the usual definition here, and then decompose into the expectation of the number of times you put the arm by time t times the gap. Some remarks here. So as we said in the above slides, there are numerous existing work targeting this model with restricted assumptions on delays. And recently, last year, there's Lansavsky paper. They gave an algorithm based on upper confidence bound achieving near optimal regret bound when the delays are unrestricted. But the motivation here is that Thompson sampling is another heuristic shown to have good empirical results, and especially shown to be robust to delays under various experiments. So despite theoretical results in the case of no delays, and I just listed some representative ones here, there's no such result in the case of unrestricted delays when you don't put restrictive assumptions. So here our goal is really to understand this scenario and how Thompson sampling used out of the box and without any adaptation behaves under delays, both theoretically with ground bounds and empirically with comprehensive experiments. So for any reward distribution with bounded means, we could, without loss of generally consider a Bernoulli bandit problem. So, and in this scenario, we consider Thompson sampling that start with a uniform prior beta 1,1 on the mean parameters of each arm. And then the Thompson sampling algorithm under this delay case is just straightforward adaptation. You just sample the zetas from the posterior distribution and play the arm with the maximum zeta. And then when you actually see the reviewed observations, you update your posteriors. So on theoretical results, so we make the following assumptions atop the model. So we assume the distribution are Bernoulli distribution and then ordered. So the arm 1 is the best arm here. And we assume each arm has a delay distribution, d1 to dk, supported on non-negative integers and infinity. So the delay could be unbounded. And the delay is sampled from this particular distribution of particular arm. And we assume, like we said previously, that the delay is independent of the rewards and past delays. And we use the following notations throughout. It's the, so d sub I of q is the q's quantile of the delay distribution of arm n. The theoretical results are decomposed into two parts. The first one is about two-arm case. So under these assumptions, with two-arm, suppose we have this IID delays for each arm. So like each time you sample your delay from the delay distribution of a particular arm, then the regret of the algorithm is bounded by this expression here. So you choose Q1 and Q2 quantiles, and then you minimize the expression. So this looks complicated, but you just, when you consider the big O order, the regret of the Bernoulli bandwidth, this delay assumption and two arms is bounded to the order of log t over the gap times these 1 over sum of the 1 over quantiles. And there's also an additional term that depends on the quantiles of delay distribution and the gap. So for example, here, if we set Q1 and Q2 to be 0.5, then the above bound depends on the medians of the delay distributions rather than the means. So a comparison with this recent paper. So they show that under their algorithm, which called successive elimination, which is just straightforward adaptation of successive elimination to the delay case, they have the following regret bound. So we see both bounds have an extra term involving linear combination of the quantiles of the delay distribution, and both are of the same big O order. So in particular, in the case of a constant delay of value d, both bounds have an additive big O of d term compared to the regret bound without delay, and this is shown already in the 2011 paper by Dudek. So when we have more than two arms, the expression looks more complicated, but the structure is kind of similar. So you have these sums of log t over the quantiles terms, and also additional terms depending on the quantiles of the delay distribution and the gap. When you simplify it, it's just this big O order is log t over the gap times this 1 over q1 plus 1 over qi term, and additional term like the two-arm case, where you have the sum of the quantiles of the optimal arm with the suboptimal arm times the disk gap. And also a comparison with this 2021 paper. So in this k greater than 2 case, their bound is the following expression. So they have this log k dependence on k. So if you consider the number of arms k to be fixed, then this bound has the same scaling as ours. But if a k can grow, then the cost of delays in their bound has a better k scaling than ours. So we have, they have logarithmic dependence on k, but we have linear dependence on k because we have the sum over the suboptimal arms. But in experiments, we have considered some moderate large k, and we don't observe any deteriorate performance of the Thompson sampling. So onto experiments. There are three main methods we want to compare. The first one is called delayed UCB1. It's in the 2013 Giordani paper. So it's just straightforward adaptation of UCB1 in delay case. And we employ random type breaking. The second one is this recent paper. They have this successive elimination with delays. It's also a straightforward adaptation of successive elimination with delays. This is shown to achieve great theoretical and empirical performance with these unrestricted delays. And the third algorithm we want to consider is the Thompson sampling. So the setup we consider are, there are 6 setups we want to consider. So the motivation is, so the first 4 are actually considered in previous papers under delays, and they have specific algorithms targeting these cases. So we just want to sort of replicate their setups and compare Thompson sampling with their proposed algorithm in those scenarios. And we also additionally consider uniform delays. And there's the final one we want to consider is non-IID delays, where your delay depending on the queue. So I will introduce this queue-based delays later in this presentation. So, so these slides show the results for fixed delays and alpha Pareto delays. So on the left is the regret plots for the fixed delay case. So some remarks here. So in the 2021 paper, they actually, so the results here are showing like successive elimination is better than the delayed UCB1 case. So that's because we have tuned this radius of the UCB. So they actually assume the radius is just square root 2 over the times you put arm. So there's no log dependence on the time. And you have to employ random type breaking here, deterministic type breaking here actually. So, so we actually just replicate their implementation in this left plot. And we see like Thompson sampling is much better than the other two. And on the right, there's another algorithm we consider called patient bandit. That's what we said in this 2020 paper, where they consider alpha Pareto delays, and they use these alpha parameters to construct upper confidence bound for this particular long tail delay distribution. And we see Thompson sampling is better than all the other three in this scenario. And there are, these are the plots for Packer loss on the left and geometric delays on the right. Some remarks here. So on the left, the Packer loss just means you don't observe your reward with a certain probability. So your delay distribution is infinite with certain probability. And this 2021 paper, they have developed an algorithm called phase successive elimination. And this algorithm is designed specifically for this Packer loss case. And we also want to compare our algorithm with that particular algorithm. So we see Thompson sampling is actually also performs the best among the four algorithms to consider. And actually, to our surprise, the straightforward delayed UCB1 is also much better than the other two. So on the right, there's UD-UCB algorithm. It's also an algorithm considering the previous paper, where they assume you have full knowledge of the delay distribution. And the reason we want to consider geometric delays is that in that paper, they also have a simulation on the geometric distribution. So we just replicate that scenario and compare our algorithm, so the Thompson sampling here, with their algorithm proposed. So we see that their algorithm actually performs better than the other two adaptation of the existing algorithms, but still Thompson sampling performs better than the UD-UCB algorithm in this case. So we also introduced a form of non-IID delay in our experiment. So we call it queue-based delay. So the motivation is like each action will go to the queue for a specific arm once we select the arm I. And if the queue is empty, then the reward is reviewed immediately. Otherwise, the reward will be reviewed when the other actions in the queue are cleared. And we assume the time to clear an action for each arm will be an exponential distribution with rate 0.1. But unfortunately, I have to say, we don't have a theoretical result on this kind of non-IID delay, and it would be interesting to consider that. So the right plot shows the Thompson performance of Thompson sampling on this queue-based delays, and we see it's much better than the other two. And on the left is just additional uniform delay distribution we consider. So conclusion, in summary, we have found Thompson sampling has good theoretical guarantee as the UCB-based counterparts under stochastic IID delays. And the empirical performance of Thompson sampling seems to be immune to the specific form of the delay. And the algorithm does not require manual tuning. For example, for UCB algorithms, you have to tune this radius. And then sometimes under different scenarios, you have different alpha parameters to tune. So future work, so I think our work is a small step toward better understanding Thompson sampling under delays. In particular, we could extend the current framework to reward-dependent delays. where the delays and rewards are sampled from a joint distribution with arbitrary dependence. So in this scenario, you still have this IID structure, but your delay distribution will be dependent on the rewards. The further extension will be non-IID delays, like the Q-based delay we introduced, and also the time-varying delays in a vaccine trial, which a lot of people consider in the current pandemic. And we actually have like a paper on this time-varying delays in a vaccine trial, but it's much harder to deal with and much harder to develop theory for that. I think that's all for today, and thank you for your attention.
Yeah, thanks a lot for the great talk. So yeah, you actually gave. I mean, you still have pretty much 2 minutes, so we could kind of like use like 3-4 minutes to ask questions right now. So if anyone has any question, yeah, please come forward. I actually have a quick question that's like tangential to the point of the paper, but do you have any sense of like why the naive UCB is doing so well in your left experiment a couple slides ago?
Let me, how do I put size? Okay.
This one, yes. Yeah.
Okay, so I think this is because the phase successive elimination algorithm, they explicitly consider this a scenario where you have like you don't observe your reward with a specific probability. I think the intuition here is that after doing these kind of experiments, these algorithms are valid for this specific scenario, but they're too conservative because they have to prove certain probability statement under this scenario. And for example, the UD-UCB and also the previous patient band algorithm, they're all like valid under these assumptions, but their confidence bounds I think are too conservative. And I think the merit of Thompson sampling is that it uses randomness to deal with these kind of things. And that's why probably is empirically performing better, even if like the theoretically they have the same regret bounds. Yeah.
That makes sense. Thanks. Anyone else has any questions for? Okay, you have a question? Yeah, Jinshuo.
So, Robert Reader is the literature. So this Thompson sampling, was it known to be perform better than UCB in the no delay setting?
Sorry, can you repeat your question?
So Thompson sampling, was it known to be to perform better than UCB in the no delay setting?
So it's like empirically.
Sorry, can you repeat the question?
Okay, so the question was like, under no delay scenario, is a Thompson sampling shown to be performing empirically better than the UCB algorithm? Yes, but like even I think under no delay case, there are also experiments showing that, and also here's with delay case you have better performance. I think the intuition is what we just said. The UCB algorithms kind of have this rigorous probability statement, and it's sometimes too conservative.
So do people understand why, without delay, why Thompson sampling perform better than UCB, despite theoretical bounds?
The theoretical bounds are the same, but like it's just empirically better than the UCB. Because there are constant dependence on the big O order. So, so even if they have like same regret bound in the big O order, they can be like different when you actually look at different scenarios. Yeah.
So there's no theoretical result on constant?
There are theoretical results where like saying under stochastic multi-arm bandit, then like your Thompson sampling has this regret bound with some big O order. Yeah. For example, like. The proof strategy actually follows here. The proof strategy actually follows the previous two papers on like no delay case. Yeah, it's just extending, adapting their proofs to delay case. Yeah. Yeah, the Agro paper. Yeah, exactly.
Right. Yeah, we can do one last question. And
do you have a sense of whether square root T minimax regret is still recoverable in this setting, or there is something that breaks down in proof?
Yeah, I think there is something breakdown in the proof. Actually, it's pretty hard to
Even
consider.
if, let's say, the delay distributions are identical across all arms, you still cannot recover square root t.
We actually didn't consider that. Yeah.
Okay, cool. So it's like 10:22 right now, so it's time for the break. But yeah, so thanks, Sam, for the great talk. So let's thank him again. Also, thanks everyone for coming to a 9 a.m. session on the last day of EC. So yeah.